Yes.
Okay, so thank you for inviting me to this. This is, I mean, I've already thanked you on Monday, but I'll thank you again. It's quite an experience. This is probably the future. And so you are pioneers, you are trailblazers in this new modality. Your workshop is on, oh, is it paused? Sorry, the screen sharing isn't working. Hang on. Can you see it now?
It was working.
Yes, yes.
You can see it. Okay.
It was working, Pedro.
It was working because on mine it said screen sharing had stopped. Anyway, so your workshop is an observational cosmology, and so what I'm presenting here may seem a little bit off topic, but I would argue that this is an interesting new possibility and that there might be more possibilities like this. And so let me give you my spiel. The idea is we're in this interesting phase of gravitational physics where the three cornerstones, which is cosmology, black holes, and gravity waves, there's a lot of activity in all of these, and they've just passed a threshold in which there's a lot of interesting stuff happening. And what is interesting is that there is now an interplay between these three things. And I'm going to talk about one example, which is what I talk about in my presentation. If you remember the binary neutron star measurement, the GW170817 measurement, showed that the speed of gravitational waves is essentially the speed of light to within 1 part in 10 to the 5. So it's essentially equal. And that has a lot of interesting implications. One of the interesting implications is it greatly reduces what kind of dark energy or models of dark energy you can have and how they interact with the gravitational field, how they interact with the metric. And one of the consequences of that, which not a people are aware of, is that in these theories that are still allowed, typically, it's not a proof, but typically black holes have no hair. Let me be very specific about this. In theories of dark energy, where this dark energy has some cosmological relevance, the energy density is of order 1, black holes will have no hair. And so then you can ask yourself, well, if the black holes have no hair, if you won't be able to see any evidence of this dark energy around these black holes, how are you going to look for it near black holes, which is kind of the point of this talk. And there's this interesting, surprising result, which is kind of obvious in hindsight, which is even though black holes may have no hair, if you perturb the black holes and you perturb the dark energy, there will be an interplay between the dark energy and the gravitational waves, and you may pick it up. In particular, you'll pick it up in the ring down of black holes at the end state where if you have a merger, for example, black holes merge and they settle down to one black hole, and they'll shed their anisotropies to settle into Kerr or Schwarzschild. They'll shed their gravitational waves, and in the spectrum of those gravitational waves, you will see signatures of this dark energy. You will see new specific discrete frequencies. They're known as quasi-normal modes associated to the dark energy. So the point that I'm making in my talk is we should go and look for those quasi-normal modes, those new frequencies associated with the dark energy. And I've shown in papers that they could be detectable with LISA down to pretty high precision. The question that you might ask is, how are you going to excite these dark energy degrees of freedom if your black holes initially don't have these degrees of freedom? And this is a whole new field of research where a number of people have been looking at this. One of the things I've been looking at is if you have a black hole or a binary system immersed in a cosmological axion field, you know that asymptotically axion field oscillates. That's what gives you the dark matter-like behavior. Those asymptotic boundary conditions generate an accumulation and accretion of dark energy around the black hole, and this accumulation of dark energy will then affect the ring down. So it's this interesting loop which connects gravitational waves, black holes, and cosmology, and the fact that you might be doing observational cosmology and that you would be looking for dark energy, which is a cosmological phenomenon, by observing black holes and gravitational waves. Okay, and I will stop there.
Thank you, Pedro. And I think Daniel has joined. Daniel, Thank you very much for being up at this time. I think it's 4 a.m. where you are. We appreciate it a lot. We had just started and Pedro gave the first summary, and I think if you can be the next one to give a summary, if you had your coffee already.
Yeah, I still need the coffee, but yeah, I'm glad to be here. I'll do my best. I might be a little slower than usual. Okay, here, let me share my screen. I just put together a few slides just to kind of quickly summarize. And there we go. Okay, so you know what I was talking about are some results in gravitational wave astrophysics and cosmology, and I was focusing on some of the more recent things we've discovered and kind of where we're headed. And to start, I think it's important just to remember where we are. At this point, we have the second catalog, GWTC2. It has 50 gravitational wave events. So in the span of 5 years, we've gone from our first detection ever in direct detection of gravitational waves in ground-based observatories to now we have a catalog of 50. And that's a very rich catalog, and the theme of what I've been talking about is what do you learn from this catalog? There are also a few exceptional events. Exceptional events, we define exceptional events as any event that is in any way surprising or different from the existing catalog. So the first event was exceptional because it was the first, but now if we get that same event again, it's not exceptional because we've actually seen a bunch of events like it. 30s are pretty common. So now our definition of exceptional evolves, and there are a number of those, and I discussed the kind of more recent exceptional events. Then I also discussed just briefly the main papers that came out of the catalog. We released these just a few months ago. These are the catalog paper, which summarizes what we've detected, the kind of current state of our knowledge of binary systems, the testing GR paper, which is more relevant to what Pedro was just talking about, and then the population paper, which is more kind of astrophysical and cosmological inference. And I'm focusing on this last paper and some of the results there. A lot of them look like this. So this is a plot of the rate density. So it's the rate of binary black hole mergers per cubic gigaparsec per year. And this is as a function of redshift. And the constraints are given by these blue shaded areas. And what your eye is supposed to be drawn to is the fact that this seems to be going up, that there are hints that the rate is going up with redshift. And as we go to higher and higher redshift, we get more and more events. And this is measured from the population we've detected so far. We're inferring this. And to draw your eye, I'm also plotting on top the star formation rate. And there's this idea that these black holes are originally formed in stars, and the stars collapse and make the black holes. So there's an expectation that the binaries probably follow something like the star formation rate, with perhaps a delay because it takes a while for the binaries to form and merge. And so you might expect it to look somewhat like this black dash curve, but we don't know. The main point here is we're starting to even be able to probe at higher redshift what the merger rate density is doing. This is very preliminary. We only have 50 events. Most of them are actually reasonably nearby. So that's why these have large uncertainties, but it's where we're headed. And it's very exciting. And these are the sorts of measurements that they're obviously quite cosmological, and they are very constraining on formation. I also discussed various, since this is kind of a cosmology focused workshop, I tried to focus somewhat on cosmology, and there are some range of interesting measurements that can be done on the cosmological side. And this is one I'm particularly excited about, having to do with the parent stability supernova gap. The gaps play a large role in our knowledge of gravitational wave astrophysics right now. This is the upper gap between about 50 and 120 solar masses. And there's no question, I argue in the talk, there's no question that there's a dearth of black holes above about 40 or 50. That's very clear in the data. That's a feature, and you can use that feature redshifts, and you can therefore use that feature to do cosmology. The gravitational waves gives you distance directly. Luminosity distance is directly measured from gravitational wave sources. The redshift of the feature gives you redshift. By combining that, you get h of z as a function of redshift, and you actually will measure that extraordinarily well to a few percent at redshift of 0.75. So pretty far out in the Hubble flow, and that's very exciting. And that's just one of many measurements that might have cosmological relevance down the road. And I just ended by pointing out that this is the beginning. We're now in this field of gravitational wave astronomy, but we're off right now. All the detectors are off there. We've just kind of given the update, and the expectation is that we'll be on, maybe if we're lucky, in June 2022. So it's a slightly longer break than we were hoping for, but things are happening. The detectors are being improved, and sometime in the next couple of years, we hope to turn back on, and we'll be much more sensitive. We expect to increase our rates by factors of, say, 2 or 3. So now we're talking about on the order of hundreds of events per year, maybe on the order of a few binary neutron stars per year, and that should be incredibly exciting. And that's, in some sense, right around the corner.
Okay, thank you, Daniel, for the summary. And Roman, now, can you summarize your talk in a few minutes, please?
Let me see if I can share my screen. Does this work? Okay, so my talk is about nonlinear corrections due to galaxy bias. And so first, I just want to make the point. So these nonlinear corrections in the power spectrum are very well known. So basically, we measure, if you only use linear theory, you can only, can you see my pointer? Probably not.
I think we are looking at the presenter point of view. So we are seeing this slide and the next slide together. And your pointer as well. We see your pointer, but we see your pointer.
Okay, that's okay. I don't know why it's doing this. But if you can see,
yes,
you can see it, then it's okay. So what are these loop bias corrections? So there are corrections because bias is nonlinear, and that's sort of natural out of structure formation. So in the power spectrum, they are very well known, but the modeling until recently has been very ad hoc. So one of our main goals here is to try to understand, if you write the general nonlinear corrections that you expect in current and future surveys to extract cosmology, what is the parametrization that you should use? What are the parameters that are most important, etc. Okay. So as I was saying, if you use even at scales k less than 0.1, these corrections are of order 10%. So definitely you have to take this into account. And so, so is this better? You can see it bigger now, or?
It is better. It's better. We can see everything big now.
Right. Okay. So, so now this is also true for the bispectrum, which I didn't get into my talk because it's already long enough. So, but here similarly, you can see, if you look at the color plots, you can see, if as you go to scales of order 0.15, you can have as big as 60% corrections to the leading order predictions. So these corrections are there, and we had to do a good job of including them in order to extract cosmology reliably. So our test in this, what we did in these two papers, basically, the first paper is more about the formalism. The second paper is about the test in the power spectrum. There is an upcoming 2 more papers, one in the bispectrum and one in cosmological parameters. But the goal here is mostly to take a big, a broad set of bias tracers. So there are 7 tracers here listed in this table. So 3 are sort of galaxies, which are modeled after Sloan surveys, and then some halos, which allows us to go to higher biases. And the goal is, so if you can see here at the bottom of this slide, there is the power spectrum. So I'm going to concentrate on the power spectrum. So there is the power spectrum of galaxies. It's to this one loop order, has, in the standard way of writing things, has 5 parameters, which are the parameters which are underlined in red. So N0 is the shot noise, deviation from Poisson shot noise. And then you can see in this gamma 1 function, there is a linear bias, there is a cubic bias, which is this gamma 2 then you have quadratic bias, B2 or gamma 2. So in the standard model, there are 5 parameters. And people usually make some assumptions which are ad hoc about these parameters. So our goal was to study with these 7 tracers, do a systematic study of what are the, parameters which are relevant and which ones are less important. And in green here in the first expression for the power spectrum, you can see you can augment the standard model of one loop bias by having this N2 parameter, which tells you that the shot noise is scale dependent. And that's what you expect because halos have a finite size. So if you basically have an exclusion effect, so if one dark matter halo is here, the other one cannot be on top of it, otherwise they would merge into we would call that a bigger halo. So there is this exclusion effect, which you can think of them naively as hard spheres, and that makes these halos cannot be randomly Poisson distributed in the sky, so they have to have some hard sphere interaction, and that induces this k-square term at low k. So that's one way in which you can basically increase make your noise description a bit better. The final term here, beta, which is also a possible extension of the one loop bias model, is to include the so-called higher derivative bias. So it's a k-square p contribution. And some people are including this, some people are not. So the question is, what of these extensions are, these 2 green terms in green, which ones are relevant and which ones are not? And so we took this expression for the one loop bias for these 7 different tracers at different redshifts, different biases. I did an extensive analysis of, how well this one loop model works. And to actually test one loop in the bias only, if you look at this first term in the power spectrum, there is a P of K here. This is the matter power spectrum. And instead of making a theoretical prediction about that, we use the measured power spectrum from the simulations. So we are only testing one loop bias and not one loop effects in the matter description. And so what we found is that if you just keep yourself to the red terms in red, which is the standard bias model, so that works very well as long as you analyze only galaxy-galaxy power spectrum and you keep to large-scale linear bias less than 2, so for moderately biased objects. Now, once you go to higher bias objects, that's not enough. And also, if you analyze together galaxy-galaxy and galaxy matter, which is important for weak lensing observations, just keeping the standard model alone is not enough. And so we study, what are the extensions that are most important. So testing this N2 parameter, the higher scale-dependent noise, or the higher derivative bias, we found that actually the extension of to having this noise be scale dependent is the most important contribution. So our recommendation basically becomes now a 6-parameter model in principle, so we can drop this beta here. Then the question is, how can we reduce this number of bias parameters when you have finite error bars? And two of the most common ways of reducing that is to use predictions for the non-local bias contributions, which are this gamma to 1 parameter in this first expression here, and the gamma 2 parameter in this capital gamma 2 propagator. And what we found is that constraining little gamma 2 by what we know already from sort of evolution from Lagrangian initial conditions, and by peak theory, we have predictions for this gamma 2. So that works very well. If you want, so that means that you reduce one parameter. If you try to reduce gamma to 1 as well here, you find that that works well for low bias objects, but it doesn't work very well in general. So that's maybe too aggressive of a prescription. So at the end of the day, basically we have a 5-parameter model with, say, no high derivative bias and a tidal field gamma 2 parameter, which can be predicted reasonably well from theory. And that seems to work for all the tracers, and including matter galaxy and galaxy power spectra. So that's our recommendation at the end of the day.
Thank you, Roman. Okay, so I think now we open for questions, everyone. So I remind you, use the raise hand feature if you can on the participant list, or write if you are co-host. So we have already a couple of questions. Let's go in order. So I think it's Zakaria. Zakaria, please correct me on your name. You can go ahead. And if you can turn on your camera during the question, I appreciate. If not, it's okay as well.
Hello. Do you hear me?
Yes. Go on.
Yeah. So hi to everyone. I have some questions to Professor Ferreira about his talk. So the first one, you said that those theories may have hair. So can you tell one comment about that? And the second one, you said theories of Einstein, Dilaton, Gauss-Bonnet don't have any interest for cosmology and so on. So what do you think about 4D Einstein Gauss-Bonnet, the new theory of Glavan and Lee? Even if there is not really, we don't have a consistent theoretical model. And the last one, we know that we have many future experiments that will allow us to constrain modified theories like Euclid and LISA. So how, for example, Euclid will allow us to constrain modified theories of gravity, or using LISA to for example, to constrain the factor of damping in the modified equation of gravitational waves, or using the waveform templates to constrain them. Thank you.
Thank you. So 3 questions, and I'll try and answer them quickly. The first one is, I think the point that I make in my talk is, if you have a theory with a cosmologically relevant scalar field, that means that a rough way of saying, roughly what that means is, it contributes to the expansion of the universe in a non-negligible way. And that theory obeys the GW170817 constraint, that is, that the speed of gravitational waves is the same as the speed of light. Then I think it's pretty general. I don't have a proof for it, but we've done a kind of an exhaustive look at the families of scalar tensor theories, that black holes will have no hair, i.e., it's not that they'll have hair, they'll have no hair. And so then you can ask the question, well, if they have no hair, how will we see any evidence of the hair? And what I mean by the hair is evidence of the scalar field around the black holes. And it turns out that you can see in the perturbations of the black hole, for while the background may be Schwarzschild or Kerr, i.e. the scalar field is a constant, so it's effectively 0. If you perturb it, you'll get perturbations in the scalar field You'll get perturbations in the gravitational field. They mix, they generally mix, and you'll get new modes, you'll get new solutions, which you have to add to the normal gravitational wave solutions. And so what you do is you go look for that. So that's how the hair comes into it. Second thing you said about was the 4D. I watched that from a distance. I watched that, you know, there was a flurry of papers on that theory. And then there were a flurry of counter papers basically saying that it's completely inconsistent and ruling it out. And so I decided never to have to look at it. So I can't give you an informed opinion about it. I've just watched it come and go from afar. Okay. The final thing is, yes, I think one of the science cases for future surveys, and for Euclid in particular, is to try and test for general relativity on large scales. And it'll do that by, I always think of it as really two things. It'll look at how lensing deviates from what you get in GR, if you get an extra correction term due to gravitational slip. And it'll see how the growth rate of structure is different compared to Newtonian collapse. So by pinning down these two things, you'll be able to say something generally about modifications to general relativity, but also quite specifically about specific theories.
So guys, first of all, I have to, even though I'm one of the organizers, I committed a faux pas, big faux pas, which I forgot to introduce our poster speakers. So I have to correct that now urgently. So please, we have Clesio. Please, can you turn on camera, say hi to people, and a couple of phrases, just what was your poster was about. Sorry about that again.
That's fine, Miguel. I'm Clesio de Bon. I'm currently an assistant professor at CBPF in Rio de Janeiro. And my presentation is only 3 minutes, so I invite you to all watch it. I'm trying to retrieve the Hubble constant using the statistical approach. The approach is known as dark siren method. So we don't know which are the galaxies, the correct galaxies where the gravitational wave event happened. So we try to get the most complete as possible, the catalog most complete possible for try to constrain H0. So this is a very hard measure to take because we need good photometric redshifts, we need good and well localized events. For now, we could actually get some of the interesting constraints for 3 new events and add to the events that we have done, Antonella Palmes and his collaborators have done before.
Okay, thank you, Clesio. Now, Hector Javier Rotua, if I'm pronouncing it correctly, please introduce yourself.
Hello, everybody. My name is Hector, and my work is about constraining reionization history using Bayesian neural network, Bayesian normalizing flow, sorry. So the idea of this work is try to use deep learning methods for doing inference in cosmology. So we use Bayesian neural networks for estimate the cosmological and some cosmological and astronomical parameters from 21 centimeter maps. And we use these Bayesian neural networks of PNN because these networks give not only predictions, but also the uncertainties of these predictions instead of the standard neural networks in which only you can get the point estimates. And in the second part, we put in the top of this BNN normalizing flows in order to get a more robust model in terms of accuracy and also reliable uncertainty estimates. Thank you.
Thank you, Javier. So I think now the next one in line is Hideki to ask the question.
Yeah, I have a quick question to Daniel. So you show the in the plot rate of binary black holes drops with high mass. So I was wondering if there is some effect to mimic this effect in the measurement. For example, if you go high mass binary black hole, the frequency wavelength of gravity wave get longer, and it may decrease the sensitivity of detectors or something. Is there something like that?
So, Hideki, that's a great question, and the answer is yes. There is. It's what we call observational selection effects. So the sensitivity of our instruments does change depending on the mass, and it's there are two things that are probably relevant to this discussion. The first is that as you go to bigger black holes, as you say, the frequency actually goes down, and that makes our detectors. As you continue to go down, you can get to a point where they're quite insensitive. But that actually only starts to happen when you get to much bigger black holes, maybe 80, 100, or beyond that. The other effect is that as you go to bigger black holes, they get louder. And so we actually detect them farther away. And so what's happening when you get around 50 solar masses, 60 solar masses for each black hole, we actually become more sensitive. And we only start becoming less sensitive when you get over 100. This was first discussed actually in a paper I wrote with Maya called Where Are LIGO's Big Black Holes? And if you look at that paper, we kind of discuss how this works, and we show that the fact that we don't, in the observed rate, we don't see many more. There's a little Chris. That's great. I hope he has some questions.
Yes, thank you very much. Yeah, I was really impressed with this evolution works and the evolution work. I just wanted to confirm my understanding. Yeah.
Yeah. So sorry. So I'll just finish on that point. I just got distracted. So there. What happens is the fact that the observed rate doesn't actually increase tells us there's something very dramatic happening at about 40 or 50 solar masses, specifically because the selection effects actually say we should see more, we should be more sensitive for a while. And instead we're seeing even fewer. And so that's part of the reason we're convinced there's a sharp drop there. But it's exactly as you say, selection effects are crucial. And for all of these statistical inferences of the population, understanding the selection is what takes a lot of the effort, and it's extremely tricky and subtle sometimes to make sure you're incorporating that properly.
Thank you.
I think little Chris realized that really this is the future, right? His next generation is where he has to pay attention. So next question is by Rogerio.
Hi, so my question is for Roman, and I want to compare your methodology with other methodologies, namely the effective field theory and also the HOD. So your method is basically the same as EFT, but maybe the gamma expansion, you don't need the counter terms. And also for HOD, can you map your parameters to HOD parameters, or at what point HOD becomes more efficient or not, although it's not first principles?
Right. So let me answer the second one first. Yes, you can map the HOD to this. So in the HOD, basically for people who are not familiar, you're putting galaxies inside halos with some occupation distribution. And basically the bias parameters of galaxies can be related to the bias parameters of the halo, that the halos that you have in your cosmology through this HOD. So if you measure the bias parameters, so all these bias parameters that I wrote down, they all exist for halos, okay? So so people have fitting formulas for them, not all of them, but not up to higher order, but this can be done. So given an HOD, I can actually, through that machinery, go from the bias parameters, large-scale bias parameters of the halos to those of the galaxies. So that can be done. The problem with the HOD is, well, it's not a problem, it's sort of a limitation. It has an advantage and a disadvantage. The advantage is that this halo formalism, it can be made to work at small scales. So it's more of a compact. I mean, if you want to push perturbation theory to very small scales, eventually it breaks down, so you cannot do it. So the HOD has the advantage that it doesn't assume perturbation theory, but it has many other assumptions which are a bit, you know, they're not probably not accurate to the level that you need to take advantage of small scales where the error bars are small. So for example, typically people assume only mass matters. So the HOD only depends on mass. You can, of course, increase that by a second parameter or a third, but the astrophysics becomes very complicated at small scale. So it's not clear that at the end of the day, you know, you can actually win by doing this HOD. So it's something that has to be checked. And of course, people are aware of this. It's a common criticism. So, whereas the perturbation theory part, you know, it's all, you know, it's basically you assume all the symmetries that you have for your bias tracers, and then everything follows basically from just you know, large scale physics, and these fluctuations are small, so you are in a sounder sort of footing. The problem is that at some point, at some scale, it breaks down, and it's not clear that by pushing this to higher and higher loops that you win, and the number of parameters increases quite a bit, as I was showing. And so it's not clear that at some scale, even if perturbation theory still works, you have to marginalize over so many parameters that you're probably not winning. So what we showed in this paper and in an upcoming paper, that is still at the one loop level, you still win. But at some point, this is gonna, you know, this is not gonna work. But it seems that we are okay until at the one loop level. Now, the comparison with the DFT, when it comes to bias, bias has always been an effective theory. So people now want to call bias effective field theory. That's fine, but bias has always been what it's been. So you write all the terms. So it's just the semantics, whether people call this EFT or not. By definition, the theory of bias has always been an effective field theory since the 1970s or so. It's just some people want to, I usually reserve that name when people do it for the matter fluctuations. In that case, there are different ways of doing that, and EFT is one of them. So then you have SPT, and you have just solving the Blasov equation. There are 3 different ways with their own assumptions. So, but yeah, so in the sense, what I wrote for bias is also what people call EFT theory of bias. It's just the basis that I use is different. I think it has some advantages. I tried to argue why of that in my talk, but it's just a mapping from one basis to another.
Thank you,
Okay.
Roman.
Thank you, Rogelio. So next question is from Caroline.
Hi, I would like to ask 3 questions for Pedro. The first one is about the error bars that you have on the time delay parameter that you used. Sorry, I cannot start my video for some reason. I don't know what's going on here. So about the time delay, I'm asking about this error bar because when you see this time delay, you can rule out many terms in the Horndeski theory. And my question would be if we are observing some alpha, which is not 0, simply because we have this intrinsic error in the time delay. So how well should this error be, and how strong are these claims? The second question is about the amplitude of the gravitational waves you use to draw conclusions for the detectability. And the question is, how do you compute this amplitude? Because we are working in, as far as I know, in a strong gravitational wave regime. So do you use perturbation theory or something else to compute that? And the final question is a bit of controversial, at least for me. I don't know if it is for the other people here, but it's about the recent claims on the reliability of the supernovae data and the evidences that the accelerated expansion are marginal. So I would like to hear your opinion on those claims.
So the first thing, I'm not completely sure I understand the first question. The point being that the electromagnetic signal and the gravitational signal arrived within a couple of seconds, okay? And we know that the events happened at about 40 megaparsecs. And so if you work out how much, how big a difference you're allowed to have between the two speeds, you find that it can't be greater than 10 to the minus 15. So I don't care that it's 1.7 second. All I know is that it's of a few seconds. It's not, for sure, it's not greater than a few seconds. And that puts it sufficiently close that it's 10 to the minus 15. 1 over 10 to the, that it's sufficiently close to 1 part in 10 to the 15, okay? So then you look at what that means in terms of the speed of gravitational waves, and what you have is you have a lot of time-dependent terms, okay? And so indeed you can tune things so that you can cancel things to be almost zero, and there's one proposal to do that. But it depends on all these other background cosmological parameters. So the kind of agnostic thing to do is say, look, if these things are so close, it's because this has to be zero. Okay. If you do that, all these terms go away. So that was statement number one. What was the second thing you asked?
About how you compute the amplitude for the gravitational waves.
Right. So it turns out that, I mean, in binary mergers, right, you have the in spiral, and then you've got the merger, and then you've got the ring down. And the in spiral, you can describe very well, incredibly well, using a form of perturbation theory. And it turns out that the ring down, you can also do incredibly well doing perturbation theory, just linear perturbation theory. In fact, it works really well all the way, almost all the way up to the merger. At some point, you have to consider higher order terms, but and so there's an art in where you cut it, and I don't think there's a complete answer on where you should cut the time series so that you're only considering the linear regime. So linear theory is okay, but there's another aspect to your question, which is the amplitude. And the amplitude, one of the crucial point here is, if you're going to see anything, the amplitude in the scalar modes has to be as big. Well, the amplitude in the scalar modes can't be zero. And that one of the things we did a few years ago is to see how the detectability depends on the amplitude of the scalar mode. And the amplitude of the scalar mode is going to depend on the process that led to excite the scalar mode. So that's a completely open question. And I think that is the question people should be answering at the moment. But you can go down to 10 to the minus 3 of the normal gravitational wave amplitude, and you could still detect something. Finally, with regards to the accelerated expansion and the supernova, I mean, we had a talk recently by the Korean group saying that if you analyze the supernova in a particular way, you get decelerated expansion. I have a colleague of mine at Oxford who very much advocates that. I think this is all. Let's put it this way. Let us put it this way. I think it's great that these people are doing this because I think they're stirring things up. I have yet to see a completely compelling case for why the supernova data are wrong. I think the supernova data were overhyped 20 years ago. In other words, I do not think we had a 3-sigma detection of an accelerated expansion in 1998, given all the systematics that we know exist now. But on the other hand, I've seen very robust rebuttals to a lot of the supernova claim, the anti-supernova claims. So I don't have an opinion.
Okay, thank you.
Okay, so next question is from Cora, please.
Yes, thank you. Hi, the question is for Roman. Hi, Roman. So perhaps I misunderstood a part of your talk, but there is a part of your talk in which you're showing consistency for bias loops between power spectrum and bispectrum for CMAS type galaxies. And yes, perhaps I misunderstood the dashed lines, but I'm seeing, so the constraints agree and they get better and I agree super well for B1 and B2, but I'm seeing sort of a 1 sigma shift for gamma 2 and gamma 1, 2. And with respect to, I think, what you expect to see from this, from your input in the simulations, but I'm not sure if that part understood correctly, and I wanted to ask you. Yeah, I forgot to mention that. I should have explained it.
so for B1, you definitely should get that answer because you have the matter, you have the galaxies, you know what is B1 by using information on matter alone, and we do get that. The other two expectations for gamma 2 and gamma 2.1 are so-called local Lagrangian assumptions, which are not necessarily correct. So it's not that we expect those. And so indeed for gamma 2, we do find that is much smaller, and this has been known already from 5 years or so. So that's what I was saying today when I was summarizing that for gamma 2, you cannot make an assumption like local Lagrangian. So we use these excursion set predictions if you want to fix gamma 2, which work very well. But those are lower than this naive expectation of local Lagrangian. And the same for gamma 2.1. So you shouldn't get those. We know that this local Lagrangian approximation for basically assumes that this tidal tensor bias is 0 at the initial conditions, meaning at past infinity. And there is no reason, if you follow a tracer back in time, these tidal biases do not vanish. So that's the physical assumption people are making in this dashed lines, which is not. I mean, it's reasonable. Deviation is not huge, but we can detect it. So you shouldn't make that assumption.
Great, that explains. Thank you.
Yeah. No
Thanks.
problem.
So next question is from Isabella. Isabella.
Hello, my question is for Professor Holmes. You showed a reconstruction of the rate of binary black hole mergers evolution. And my question is, the necessary exclusion of the low signal to noise ratio events doesn't deform this observed distribution? And how do you account for that?
Yeah, okay, so that's a great question. And it's actually related to Hideki's question earlier, I think, which is, again, this is a question of selection and what binaries do we detect and what binaries do we miss? And you're absolutely right that we have a threshold, and for events that are low SNR, we don't, I mean, they may exist in our data, but we don't call them confident detections, and we don't put them in our sample. And so that's something that we have to account for. And in particular, and this is where you're heading, the more distant events are the ones with the lowest SNR. So those are the ones you worry that you miss. And so you have to be very careful to make sure that you understand how your selection is coming into, your inference. And so that's something we do spend some time on. We're actually somewhat conservative in the catalog as to what we call events. But the key thing we do is we do what we call injection studies. So we put in fake events into our real data, and we put in many, like hundreds of thousands of events in the ideal case, all over the mass distribution for all distances, and we run the full detection pipeline through them, on them, and we get what we call misfound statistics, and we really carefully characterize what our sensitivity is. And then we use that to infer our population statistics. And so when we talk about things like redshift evolution, it's very critical that we understand our sensitivity as a function of redshift. And so it's something, a lot of our effort goes into exactly addressing that question of how well are you detecting low SNR events, especially as a function of mass, and how do you incorporate that properly? And so, as you can see, I mean, in the plot so far, there's still large error bars, and a lot of it has to do with we don't have that many events, and our sensitivity isn't that great, compared to where we hope we can go. And so we're not incredibly sensitive at high redshift yet, unless we get to bigger black holes. But that will change. But yeah, that's an excellent question.
Okay, thank you.
Thank you. So I think now next question is from Roman, actually, because he cannot raise his hand as a co-host. Roman?
Yeah, yeah. Thanks, Cora. She told me that that's the reason. I was looking for the raised hand. It's like it disappeared.
It's a limitation. It's a limitation of Zoom. If you go to Zoom webpage, there's many people requesting this feature, but you know. Right.
Okay, so I'm gonna take advantage and ask one question to Daniel and one to Pedro. So Daniel, so in your talk you mentioned that so this thing that this in principle this event that can land in the mass gap could actually be the most massive guy can be above the mass gap and the least massive below the mass gap, which is I mean, that's pretty amazing. So is there any theoretical understanding of you know, how many of these events you should have, or this is something that, since I'm not in this field, I'm asking probably a naive question, is something that it was only arose because of LIGO, or people did expect to see this very extreme mass ratios events with one intermediate and one.
Yeah, so the short version is I don't think people had really thought it through enough to make concrete predictions about those sorts of events. And so just, you know, to clarify what we're talking about, so this is the event GW 190521, which is the event where both components are thought to be in this pair instability supernova mass gap at about 65 and 85 solar masses each. So that's by far the most massive binary. And in a recent paper with Maya Fischbach, we argue that the analysis for that binary, the LIGO, the artificial LIGO Virgo analysis, assumes the priors are uninformative. So it assumes that we don't know anything about the rest of the population. And if we do that, then we find these two masses. And what we argue is the rest of the population shows pretty clearly that there are a lot fewer events at high mass. And if you use that prior on the secondary black hole, you assume that the secondary, because it's a very big, to go from we've never detected any big black holes to now we've detected two is kind of a big jump. So we say, why don't we apply the population prior? That's the proper way to do this analysis. And if we apply that to the less massive black hole, we of course find that it's lower mass. But what the data constrains is the total mass. So if you lower the mass of the secondary, you find that the primary goes to higher mass and in fact comes up so high that it's no longer in the gap. And you end up with what we call a straddling binary that has components on both sides of the gap. And, you know, Roman, like people have definitely predicted that there should be black holes on the other side of the gap, that there would be this pair instability supernova process. But once you get to big enough stars, pair instability won't, you know, in some sense, blow the star up before it collapses. And so you'll just directly collapse to a black hole again. And so there have been predictions that there should be black holes above the gap. There are, of course, black holes below the gap. There haven't been specific predictions of pairing one of each, but you know, we would argue maybe that's not that shocking. Personally, I would argue it's a lot less shocking than the idea that we suddenly have two black holes that are firmly in the gap, which is really something we haven't expected astrophysically. There are tons of papers saying that won't happen. But the truth is right now it's all quite fuzzy. And so I would claim of everything we've detected so far, this is the most exciting event. I mean, no matter how you interpret it, it's really new. It's somewhat surprising. You know, we'll detect more. I mean, we should detect more of these sorts of things, and then we'll know, are they really in the gap or are they really straddling the gap, and you know, what happens next. And I'll just mention from the cosmology side, there's some other work. This is led by Jose Maria Escriaga, where we look at how to use the black holes on the other side of the gap, what we call far side black holes, to do cosmology. And those are also interesting, and those also might imprint the feature of the gap, but the upper end of the gap. And so those you detect very far away. Those you can also detect with LISA. It's a very interesting population. And so we're kind of excited, you know, here's yet another, you know, way to get a handle on cosmology through gravitational wave sources. So but we'll see. Maybe this is the first one, or maybe they really are two black holes in the gap and we'll never detect any far side black holes. We don't know. I mean,
so Roman, you had a second question?
Yeah, a second question to Pedro. So in these theories of modified gravity, so that you talked about, are they, so do you have issues with strong coupling, and this, do you have to somehow get them screening mechanism into play, or is this not an issue? What's the status of that?
So these are just normal scalar tensor theories, right? And so you could have screening. Indeed, you could have screening, and generally well, we can discuss what generally means. Generally, you will have screening, but it doesn't affect the argument that I have. In other words, it doesn't affect the constraint from the speed of gravitational wave. It doesn't. So there are various stages in this argument. The first stage is, does the GW 1708-17 constraint apply? Screening doesn't come into that. Okay. Then, do these black holes have hair or not? Screening also does not affect, if anything, it just would, most definitely it does not affect that, because black holes have no hair, so there's no screening around them. And if you're asking a more fundamental problem, which is, the strong coupling problem, the kind of problems that they see with Galileans or massive gravities, yeah, I don't think that's an issue. I mean, you will have a range of scalar tensor theories where that is not a problem. So you could throw that in as well. And recently, one of my ex-postdocs has been looking at that, as you throw in those kind of constraints, those strong coupling positivity constraints, and that will limit it most, but it actually doesn't cut into the space of theories that you get out of this. So I don't see it as an issue.
So I have a question now, because we are running a little bit in the hour and I still have some questions. So any of the speakers have to leave abruptly?
I have to leave in about 5 minutes.
Okay. So I have myself a question for Daniel, which is, when you're trying to use the mass gap to measure, as a new observable from the standard sirens, I mean, the mass gap is not very precisely determined from the astrophysics, right? As you said, it's around 50, around 120. And how this theoretical uncertainty affects your measurement, and how could we improve on this theoretical uncertainty? This is more astrophysical, but what's the prospect on improving? Can it be sharp really at some point?
Yeah. So, okay. So great. And so there is, I mean, we are in effect saying we want to use this, feature, but it's really a statistical analysis. So we're doing a population analysis where we kind of characterize the gap, and we characterize it maybe your power law with the taper. And then the question is, how well do you constrain those parameters? And we do that simultaneously with with redshift, and can infer things. So our ability to constrain is, even if it's kind of a taper, we can actually constrain the parameters surprisingly well. And a lot of that has to do with the fact that our sensitivity increases, with mass so dramatically that the fact, even if the population, it only looks like, oh, it's kind of dribbling off, since we would have expected it to increase so much, we actually end up with quite a good constraint. And we don't need it to be sharp. But the main message here is, this is really phenomenology. So this is more like supernovae cosmology than standard siren cosmology. And that's a little unfortunate. One of the great things about standard sirens is they're just calibrated by general relativity. But now what we would say is, you can observe a gap, you can see this feature at low redshift, and if you assume that this feature does not evolve with redshift, then you can use it to do cosmology. And that's the assumption we make. And then if you do that, we show how well you can do. We say it's reasonable to assume that, because this is apparent stability. So, the mass of the electron doesn't change with redshift. And because of that, why would you expect the feature to change with redshift? But there may be metallicity dependence. There are arguments that say the metallicity shouldn't matter that much. But this starts to sound a little bit more like the supernova game, where there are lots of potential systematics that you could worry about. And those systematics are, of great concern to the measurement. And so it's not really, I mean, I can talk about the theory and say, the theory says this should be a powerful method, but at the end of the day, it'll really be, the observations. And then we'll have to look and say, do we have evidence that there's a metallicity dependence to this? And we'll be able to study that and find out. But, behind all of that, I'm surprised how well we measure features. And it turns out, any drop is actually measured much better than a bump. It's a statistical thing where, if you're just measuring the edge of a distribution, you do better. And we actually quantify that. And in this recent paper with Jose, we quantify that using some help that Maya gave us. So,
okay.
Yeah.
Thanks. So there was Renan and Mustafa. Anyone is asking to Pedro because he has to leave?
I think it involves Pedro, and I also actually need to run to another telecon right now.
So,
yeah.
As quickly,
so,
yes, and let me see.
Yeah, sure. So actually, it's a comment that I have about a question that I think Caroline asked. And about supernovae and involvement in cosmic acceleration or dark energy. So I think, so in addition to the answer that Pedro gave and that addressed the question, I think it's also worth mentioning, since we have folks here that are new to the field or or not specialized in cosmic acceleration and dark energy. So it's worth saying that even if all the supernova things turn out to be not right, let's say. And we do see a few papers from time to time about this. Like, I think even if the supernova is not, cannot be used for cosmic acceleration, yet cosmic acceleration is supported by other probes like CMB, large scale structure, and BAO. So this is, I think this is worth mentioning for, in addition to what was said. That's my only comment. Thanks. We can't hear you. You are muted, Miguel.
Sorry, Renan. I think you have the last question. And
yes.
Pedro, feel free to go if you really need to. Sorry about we're late. Go on, Renan.
Is to Roman. Hi. First, why to go to one loop in both power and bispectrum, given that they are of different order in linear delta, namely 4 and 6. Related to that, up to which order I should use in the covariance matrix. Basically, what I want to understand is up to which order I should go in this joint analysis of different endpoint functions.
Yes, well, you shouldn't, it's not, as I was trying to argue from maybe showing these two plots that I showed today, that the way it works is not by order in delta that matters, but it's the tree versus loop. So the tree gives you the large scale contribution at R, or K going to 0. And then you have the one loop contribution. And they kick in always at the same scale because the ratio of the one loop to the tree is always K, the amplitude of fluctuations. So it's the same physics that controls the ratio of the one loop to tree in the power spectrum and in the bispectrum and in the tri-spectrum and in all the endpoint functions. So the right thing to do is to consider things at a given loop order. And for the reason that you wouldn't use just linear theory to analyze the power spectrum, you shouldn't use second order theory to analyze the bispectrum. So it's just that simple. I didn't understand the second part of your question. Sorry. Was it about the covariance matrix? I didn't get it.
Yes. How to define the order I should go into the covariance matrix?
Yes. So the covariance, you mean the cross covariance between P and B, or?
Yes, for instance. Yes, in this joint analysis of different endpoint. Yeah.
Yeah, so that's actually a complicated question. So you should, yeah, for real surveys, it's also the importance, there is a shot noise contribution, which is very important typically. And so it's not, so you should take into consideration the cross covariance metrics computed to the order in which you will see that if you compute inconsistency, the metrics become singular. And it's important to make these metrics regular, that you include the shot noise and you include also the next to leading corrections in the covariance. But it's not a trivial thing, and we are actually trying to understand this better at the moment. Yeah.
Thank you. So I don't see any more hands, and we are already running a bit late now. So you put your hand up at some point, but then you load, right? I don't know. Okay.
My question was answered before, so thanks.
Okay, very good. So thank you all for joining us here in this session. We come back in 2 hours, sorry, at 2 p.m., almost 2 hours from now, for the last session of the second session of the day. Thank you all again, and see you in the afternoon if you can make it. Thanks to the speakers, thank the posters, thank the questions. That's great.
Thank you. Bye.